Now we consider scattering by an attractive square-well potential and attempt to compute, estimate the phase shift of the partial waves. Now consider a spherically symmetric potential which depends only on the radial distance and is defined by V of r equal to minus V0 for radial distance from 0 to a value a, which is a range of the potential, and V of r is equal to 0 for all values of r greater than a. And this is shown by this red line in this figure. The radial part of the Schrodinger equation is given by equation 1.2. And if we restrict ourselves to the L is equal to 0 partial wave, that is the S wave only, this equation becomes d square by dr square of r0, because we are taking L is equal to 0, plus 2 by r times dr0 by dr plus 2m E minus VR by h bar square times R0 of R equals 0. Now for R between 0 and A, we have the potential equal to minus V0, and substituting that over here in equation 1.3, we get this equation, where this quantity alpha square is defined to be equal to 2m by h bar square times E minus the value of the potential there, which is minus V0, and therefore alpha square will be equal to 2m by h bar square times E plus V0. And this has solutions given by R0 R equal to a linear combination of the spherical Bessel function J0 and the spherical Neumann function N0. Here A and B are coefficients defining the linear combination. Now R is between 0 and A, and therefore this solution should be applicable in that region. That is applicable for R is equal to 0 as well. Now, as we have already seen in the earlier lecture, the spherical Neumann function diverges at R is equal to 0. And therefore, we have to take B equal to 0 if we want a solution that is regular or finite at R is equal to 0 as well. So in that case, the solution will be A times J0 alpha R by setting B is equal to 0. Now, J0x is sin x by x, and therefore R0R is equal to A times sin alpha R by alpha R. Now for R greater than A, potential is 0, and the Schrodinger equation becomes this. So instead of alpha square, we have k square here, and that k square is equal to 2me by h bar square, since b is 0 here. And the general solution to this equation is again a linear combination of the spherical Bessel function and the spherical Neumann function. Now in this case, the solution is applicable to values of R greater than A. So we do not have the requirement that this solution be a solution at R is equal to 0, and therefore we can include the Neumann function also here. Now J0 kr is sin kr by kr, and Neumann function N0 kr is minus of cosine kr by kr. And writing this coefficient small a as a0 cos delta 0 and small b as a0 sin delta 0, the solution R0R can be written as a0 times sin kr plus delta 0 by kr. So this is the phase shift for the S wave because of the scattering. So this gives us the solution for r greater than a, and this equation gives us the solution for r between 0 and a. And since this is a solution of the Schrodinger equation, these two solutions should match at the boundary. Boundary is given by r is equal to a. Not just the wave function, its first derivative should also match. So matching these two solutions at r is equal to a gives this condition, and matching the derivatives at r is equal to a gives this condition. And dividing this condition by this, we will get the equation quote Ka plus delta 0 equal to alpha by K quote alpha A. And taking the inverse, this simply becomes tan of Ka plus delta 0 equals K by alpha tan of alpha A. Now we can use this trigonometric identity for tan A plus B, and substituting that over here and doing rearrangements, we get the final equation for the phase shift of the S wave, tan delta 0 equal to K minus alpha quote alpha A tan Ka by K tan Ka plus alpha quote alpha A. Now we consider low energy scattering, that is a situation where the energy of the incoming particle E is extremely small. So E tends to 0 limit. So in that case, K also tends to 0, because K is defined to be square root of 2m E by h bar square. Now alpha was defined to be 2m E plus V0 by h bar square to the power half. Now K is extremely small, and if V0 and A are such that quote alpha A is a finite quantity, then since K is less than since K is extremely small, Ka will also be very small because A is finite, and tan Ka can be approximated as Ka. Now this factor K tan Ka plus alpha quote alpha A can be written in the following way. Tan Ka is like Ka for small values of K, and alpha quote alpha A is finite, and alpha is also seen to be finite. Then alpha quote alpha A is simply alpha quote alpha A, and K tan Ka for small values of K can be written as K times tan Ka is Ka, so K square A. Now the lowest order term over here is alpha quote alpha A, because the second term is of order K square. Now using this in equation 3.2, we have in the numerator the first term is already K, and quote alpha A is finite, and therefore we will have alpha quote alpha A here. Then tan Ka can be written as Ka, and in the denominator we can neglect this term and write only alpha quote alpha A. Then tan delta 0 is approximated as, for small values of K, by this equation, which gets simplified to Ka times tan alpha A by alpha A minus 1. Now sine square delta 0 can be written as 1 by cosec square delta 0. So cosec square can be written as 1 plus cot square delta 0. Now cot square delta 0 is 1 by tan square delta 0, and we can use equation 3.3 to substitute for tan delta 0. So substituting that and simplifying, we will get this equation, and the final solution is sine square delta 0 is k square a square times 1 minus tan alpha a by alpha a, the whole square. Then the S wave scattering result is sigma 0, that is a contribution from the S wave only, which is 4 pi by k square times sine square delta 0, and sine square delta 0 can be replaced by this. So the scattering cross section for extremely small energies can be given by this equation. Now we consider what are called resonances. The total scattering cross section can be written as the sum of scattering cross sections from individual partial waves. We call them the contribution from individual or L partial wave as sigma L, and then the total scattering cross section is sum over L running from 0 to infinity of sigma L, and the individual scattering cross section is given by 4 pi by k square 2L plus 1 sine square delta L. Now as k tend to 0, as we have already seen, the dominant contribution comes from sigma 0. That is the L equal to 0 partial wave, the S wave. However, there may be values of k for which a particular delta L is such that sine square delta L is 1. Then the corresponding partial wave dominates the contribution to sigma, and this will be characterized by a narrow peak about the corresponding energy, and such a peak corresponds to what is called a resonance. And the form of this peak in the scattering cross section is given by what is called the Breit-Wigner formula, which is obtained as follows. So a resonance occurs when the phase shift of that particular partial wave is such that sine square delta L becomes up close to 1. So that happens if, as energy changes, delta L crosses pi by 2, because at that point then sine pi by 2 is 1 and sine square pi by 2 is 1. Now if we consider the L is equal to 0 partial wave, and at resonance energy denoted by say ER, then the corresponding phase shift delta is given by delta 0 at ER. We will have sine square delta 0 ER is equal to 1. So that is the one that corresponds to the resonance energy. So if sine square delta 0 is 1, then obviously cos square delta 0 is 1 minus sine square delta 0, which should be 0. Or in other words, cos of delta 0 should be 0. Now for energies close to the resonance, that is E approximately same as ER, we can use a Taylor expansion to write delta 0 E or sine of delta 0 E. So which can be written as the 0th order term will be at E is equal to ER. So that's given by sine delta 0 ER plus derivative of this function times E minus ER. So derivative will be cosine of delta 0 ER times derivative of delta 0 with respect to E at ER times E minus ER plus the other terms of order E minus ER square. Now cosine of delta 0 is 0, that we have seen already, and therefore the lowest order contribution is written as sine of delta 0 ER. and the next higher order contribution is 0. So we are neglecting only terms of order E minus ER square here. Now we can do a similar Taylor expansion for cosine of delta 0. So the 0th order term is cosine of delta 0 ER, which is 0. And the first order term would be derivative of this times E minus ER. But derivative is minus sine of delta 0 evaluated at ER times derivative of delta 0 evaluated at ER times E minus ER. So the lowest order contribution, the contributions up to order E minus ER is given by sine minus sine delta 0 ER times derivative of the phase shift delta 0 at ER. Now, if we call times E minus ER. Now, if we call derivative of delta 0 at ER as 2 by gamma, then cosine of delta 0 E up to first order in E minus ER is equal to minus 2 by gamma sine delta 0 ER times E minus ER. And sine delta 0, as we have already obtained, is sine of delta 0 ER. Now, quot delta 0 E is cosine delta 0 minus sine delta 0, which using this equation simply becomes minus 2 by gamma times E minus ER. Now, sine square delta 0 can be written as 1 by cosec square delta 0. Again, cosec square is 1 plus cot square delta 0. And substituting for cot square from equation 4.3, we get the equation sine square delta 0 is approximately gamma square by 4 divided by gamma square by 4 plus E minus ER the whole square. And the S wave contribution to the total scattering cross section is 4 pi by k square times sine square delta 0 and is given by this approximated form. So this represents the resonant peak at energy E equal to ER. As E becomes goes far away from ER, this dies off, and at E equal to ER, this has a maximum given by 4 pi by k square. And this formula is called the Breit-Wigner formula. Now we define the scattering length denoted by the symbol A and is defined as the E tend to 0 limit of minus of the scattering amplitude F. Now as E tend to 0, only S wave undergoes scattering, and therefore F of theta is simply the contribution from the S wave, which is F0 theta, which is given by 1 by k times e to the power I delta 0 times sine of delta 0. Now for a weak scattering potential V of R, the phase shift delta 0 will be small, so that at 0th order we can replace e to the power I delta 0 by 1 and sine delta 0 by delta 0. That's because delta 0 is extremely small in the case of weak scattering potential. Then A, which is the limit E tend to 0 of F0 of theta, which is 1 by k e to the power I delta 0 sine delta 0, can now be approximated as limit E tend to 0. Now e to the power I delta 0 is 1 and sine delta 0 is delta, and this will become limit E tend to 0 of minus delta 0 by k. So that means as E tend to 0, or in other words as k tend to 0, delta 0 goes like minus k times A, otherwise this limit will not exist. and with A being a finite number. Then the value of the scattering cross section as E tend to 0 is simply the contribution from the S wave, and that is sigma 0 E tend to 0, which is 4 pi by k square sine square delta 0. And since delta 0 as k tend to 0 or E tend to 0 is like minus k, its square goes like k square a square, and the scattering cross section is simply given by 4 pi a square. So the scattering length A can be used to obtain the scattering cross section for extremely small energy scattering cross section. Now we consider a strategy for computing the phase shifts under certain conditions. Now, considering a spherically symmetric potential, the radial equation for scattering is given by equation 6.1. Now, the quantity k square here is 2me by h bar square. Vr is a scattering potential, which is a function only of the radial distance, and L is equal to the angular momentum quantum number, and this corresponds to the Lth partial wave. Now writing the radial function RLR as VLR by KR, equation 6.1 gets simplified to this form: d square VL by dr square plus k square minus 2mvr by h bar square minus L times L plus 1 by r square multiplying VL is equal to 0. Now we have already seen that the solution to this equation is given as a linear combination of as r tend to infinity is given as a linear combination of the spherical Bessel function and the spherical Neumann function NL. So the solution to this equation as r tend to infinity is a constant multiplying JLKR as r tend to infinity plus another constant multiplying NLKR as KR tend to infinity. Now writing the coefficients as AL cos delta L and minus AL sin delta L, we can write RL R as r tend to infinity as from the asymptotic forms of JL and NL, we get AL times sin KR minus L pi by 2 plus delta L by KR, where delta L is a phase shift of the Lth partial wave. Now, from this definition of VLR, we see that VL of R is KR times RLR. And therefore, it's as r tend to infinity, VLR is limit r tend to infinity of KR RLR. But RLR is given by equation 6.3. Multiplying it with KR gives AL sin KR minus L pi by 2 plus delta L. Now, if we set V equal to 0 in this equation, we have a solution which is applicable everywhere, and we know that the solution is given by a linear combination of spherical Bessel function and spherical Neumann function, and it should be valid in R at r equal to 0 as well. But the spherical Neumann function diverges at r is equal to 0, and therefore a solution that is valid everywhere that is valid also at r is equal to 0 should not contain the spherical Neumann function. So for V is equal to 0, the solution of equation 6.1 is simply the spherical Bessel function JLKR multiplied by a constant AL. Now writing RL equal to UL by KR in this case, this equation with VR is equal to 0 gets modified to d square UL by dr square plus k square minus L into L plus 1 by R square times UL is equal to 0. Now we already know the form of RLR. So ULR is KR times RLR from this definition. So we need to multiply it with that. So AL times KR JL KR. Now as R tend to infinity, we can use the asymptotic form of JL KR, which is like sine KR minus L pi by 2 by KR. So since we multiply it with KR, we get UL as R tend to infinity as AL times sine KR minus L pi by 2. Now, we multiply this equation with UL and this equation with VL and subtract the first one from this, we get the following result. The terms other than these ones gets cancelled and we get VL d square UL by dr square minus UL times d square VL by dr square is equal to minus 2 mv by h bar square times UL VL. Now this can be written as d by dr of VL dUL by dr minus UL times dVL by dr. Now we can integrate this equation from R is equal to 0 to say some finite value R. Since this is a derivative, its integral is simply the term in the square brackets and evaluating those at those two limits and noting that UL and VL at R is equal to 0 are 0, and that is because RL0 is finite and UL is given by KR times RL. Now at R equal to 0, RL is finite. So when it is multiplied by KR with R equal to 0, this becomes 0. And similarly V0. So since both of them are 0 at R equal to 0, the left hand side will simply becomes this quantity evaluated at R. So that is this one is equal to minus 2m by h bar square, then integral of the remaining quantity from 0 to R, dr dash vr dash ulr dash times vlr dash. Now as R tend to infinity, on the left hand side we have VL and UL as functions of R, and as R tend to infinity we can use the asymptotic forms of VLR and ULR, and they are given by this equation. For UL it's given by this, and for VL it's given by this equation. This equation. So substituting them over there, we get the simplified form of so that is this equation, and this equation. And we also have to use the derivatives of UL and VL. So using that and simplifying, we will get AL square K times sine delta L equal to minus 2m by h bar square from 0 to infinity dr of V of R ULR VLR. And this is because on the left hand side we are taking the R tend to infinity limit, and therefore on the right hand side the integration can be extended from 0 to infinity without affecting the integral much. Now at higher energies and weak potentials, that is for larger values of L and for smaller values of the potential, the phase shifts will be very small and we may approximate VL as approximately equal to UL, because UL is a solution corresponding to the potential equal to 0, and VL is the solution corresponding to a non-zero potential. And if the potential is extremely small and the L value of the partial wave is very large, then it is not going to be affected much by the scattering potential, and therefore the solution VL is going to be approximately the same as the solution with the potential equal to 0. And we know the form of the solution with potential equal to 0. It's given by ALKR times JLKR. So substituting for VL with this form in equation 7.4, we have this sine square delta L equal to minus 2mk by h bar square, and from 0 to infinity dr, and this r square coming from the fact that UL has a form like this and VL has a form like that. So kr square, so k square r square and al square. So al square gets cancelled by this term, and there is a k square here, but 1k is on the left hand side also, so there is only 1k remaining on the right hand side. So this r square appears here, then Vr, then this factors of JL, one for UL and one for VL, so JL KR square. So this gives us with an equation to compute the phase shift of the Lth partial wave delta L. So sine delta L is given by this integral. Now this spherical Bessel function JL is related to the Bessel function of order L plus half by this formula. So substituting that over here, we have sine delta L is equal to minus pi m by h bar square times integral of r Vr j L plus half kr square from 0 to infinity. Now further, since delta L is very small, we may approximate sine delta L by delta L, and this integral then directly estimates the phase shift, which may be used to compute the scattering cross section.